Good morning. Uh, Welcome to section 5.1, the natural logarithmic functions differentiation. It's going to be a fun time. We're going to answer some questions from a previous chapter. The meat of the material for calculus is actually finished. We have three parts to it. You have the limits, you have the derivatives, and you have integration. Chapter 5 is the last major chapter. After this, we'll discuss some minor topics and stuff. But the reason we talk about it last is it fills in some gaps because there's some functions we haven't discussed yet. And we're going to discuss how to integrate these functions. We're going to discuss how to take a derivative of these functions. And these functions will fill in a lot of the missing pieces for things that have been discussed in other classes like Algebra 2 and allow us to integrate more and more complex functions or take derivatives of more and more complex functions. It also provides a great review because since it combines derivatives and integrals into one chapter, we'll have some derivative practice and some integral practice before we finish the year. So let's take a look at 5.1. First thing to note, in 5.1, your homework assignment is going to be 2 parts. So we'll have one part today and one part tomorrow. It's on page 331 in the textbook or on page 355 in the PDF. And that is 7 through 35 odds and 39 through 53 odds. That's the first part. Okay, so at this point, I want to discuss some topics from algebra that we may not remember, and therefore give us a good way to see how these all fit together. So, first thing I want to mention is the definition of a natural log. Now, there's an algebra way to talk about this function and a calculus way to talk about this function. I'm going to talk about the algebra way first. To talk about the algebra way is a little bit harder because it really doesn't fit very well. So we talk about in algebra how we have exponential functions like e to the x power or 3 to the x power or negative 2 to the x power. And we talk about how these functions interact. We talk about how they work. And then we talk about how we can use an inverse to turn these from e to the x into the natural log of x, from 3 to the x power to the log base 3 of x, from negative 2 to the x power to log base negative 2 of x. And so we talk about an inverse effect creating these functions. And so we define the natural log by looking at e to the x. We define log base 3 by looking at 3 to the power of x. We define log base negative 2 by looking at negative 2 to the power of x. It allows us to look at these functions in different ways. But we define them by the power functions because power functions exist naturally in algebra. It only makes sense that you can multiply things a number of times and get a result. Whereas the log kind of doesn't make any sense. It doesn't really fit in anywhere else. Now, the calculus way actually provides a great definition for what an actual logarithm is. And it does so by looking at a very specific example. What is the integral of 1 over x? Now, if you remember back in the day, we would solve an integral with the power like this by first converting it into power form, so x to negative first power dx. And then we would actually do the power rule. But if you do the power rule, something weird happens. You'd start by adding 1 to the power, which makes it a 0, and then dividing by the new power. Which this doesn't make sense, because having a 0 power means the x will disappear, and dividing by 0 is not allowed. And furthermore, it makes even less sense because you can't work backwards. You can't take this function and take its derivative and get back to here, because I would still end up dividing by 0, and when you divide by 0, nothing works. So it turns out that this function is actually solved by looking at a natural logarithm. So the integral of 1 over x is defined as equal to the natural log of x plus c. So in this case, what this tells us is the natural logarithmic function, ln of x, is equal to the area under the curve 1 over x. Now, a few things to note about the natural logarithmic function if you don't remember. 1, to use a natural logarithmic function, x has to be greater than 0. That is because if you think back to what the graph of a logarithmic function looks like, we have this is our natural logarithmic function. Oh, sorry, this is our exponential function 1 over x. And so we're talking about the area under this curve. If we try to go to 0, well, this thing's going up to infinity, and so we end up having an asymptote here. So we can't get to 0. And then if you start talking about what does it look like when we have an actual logarithmic function, the logarithmic function actually starts and stops in just the first quadrant. Or the right-hand side, I should say. And so this is the natural logarithmic function. And so you can see how there's nothing to the left of 0, which is why we have to have a domain of x is greater than 0. So, as you can see, the area under this curve is representative of this function. So, this is a pretty basic property listed right here in the definition of the natural logarithmic function. It's important to note that there is still the connection to previous material, where you have e and natural log as opposite functions of each other, as inverse functions of each other. Okay. Next. The big one for your homework tonight is going to be these properties. Because to start off with, before we start talking about integrals and derivatives, we need to make sure we have a firm foundation on what some of the properties are. Because otherwise, it's really hard to answer the question of where the actual properties come from. Because you can't integrate something properly if you can't rewrite it in a form that can be integrated. So let's take a look. We have here from theorem 5.1. These are properties of the natural log. So, first property. You have a domain from 0 to infinity, non-inclusive, and a range from negative infinity to infinity. Again, if you look at the graph of this function, that should make a lot of sense. Because if we have a graph of the function, we can clearly see that the x values only start working at 0, or just after 0, but the y values always have an answer. So that's property number 1. Property number 2, which is a fun one. It is a continuous function in this domain. So you notice there's no asymptotes, there's no holes listed in this function. It is always increasing. Meaning that if I pick a number to the left and then pick a number to the right one will always be slightly bigger. Sometimes a lot bigger. But that's, remember, the definition of increasing. Also, if we think back to chapter 2, since it is increasing, that means its derivative will always be positive. And then finally, it is 1-to-1. In other words, it passes the horizontal line test. So every time we have a function, or every time we have an x value, it has exactly 1 y, and every time it has exactly 1 y, it has exactly 1 x that goes to it. And then finally 3, concave down. Now, remember, from these two pieces, this is talking about the first derivative, back from chapter 2, and this is talking about the second derivative. And both describe this picture. right? Concave down means it's like a bowl, or sorry, like a hill as opposed to a bowl. And so since it's concave down, we know it's going downwards, it's opening downwards. Whereas increasing means that over time it always goes up. So there's theorem 5.1. And the big one for tonight, theorem 5.2. These are ones that are specific to the natural logarithm. However, for theorem 5.2, these are true for all logarithmic functions. So this is functions of any base, of any style. So it could be log base e, like the natural logarithmic function. It could be log base 10, like the log function. Or it could be any other log function when it's talking about these. So, 1. First thing to mention, the natural log of 1 is equal to 0. And in fact, this is true for any function that's a logarithmic function. So if you put log base 10 of 1, it'd still be 0. 2. The natural log of a times b is equal to the natural log of a plus the natural log of b. This is a big one for us because typically when we talk about derivatives and integrals, multiplication means I have to do something fancy. But when it comes to addition, I can split things apart and do them in separate steps. And so this is a big way to take a function that looks nasty and break it into components that probably have derivatives or integrals that can be done. Number 3, powers. If you have inside the logarithmic function, if you have a to the b power, this becomes b natural log of a. So the power essentially moves out to the front. And then finally, number 4, division becomes subtraction. The vast majority of your homework tonight is just using these 4 properties in a variety of ways. That's really important to know because it can't be understated that if you can't do the logarithmic properties, you can't continue on for the most of this chapter. Because these functions, if you don't get how they fit together, then you simply can't use them, which is a big issue. So let's look at some examples of how we might use this kind of information. So let's do the 3 examples we have in the text, and I'll pull another one from the book afterwards, from the homework section. All right, so ln of 10 over 9 is our first example. Ln of the square root of 3x plus 2 as our second example. Our third example, ln of 6x over 5. And then for our fourth example, we have the nasty one, ln of x squared plus 3 squared over x times the cube root of x squared plus 1. Okay, these are referred to as expansion problems. You'll typically see in your instructions, they'll say expand the logarithm. And what it means is use the properties to break these 4 things down as far as they will go. So if there's the first example, I have division. According to our rule, division from number 4 becomes subtraction. And so the top piece is written first, the bottom piece is written second, and the subtraction sign is between them. So if I want to expand this logarithm, I would write ln of 10 minus ln of 9. Since there's no other operation, there's no multiplication, there's no powers, there's no division, and there's no ones, this is the final solution. Let's compare that to b. So for b, it helps to rewrite this first. So we rewrite this as the natural log of 3x plus 2 to the 1/2 power. Why do I do that? Well, because I have a rule that fixes powers. So since I have something to a 1/2 power, what this tells me is this becomes 1/2 natural log of 3x plus 2. Now, You might ask, is there anything else we can do? We do have multiplication, 3 times x, so can I split this apart? And the answer is no. Because of the plus 2 is being applied to the 3x. If I could factor a 3 out, then I could split it apart. If I could factor anything else out, because remember, this is a times b, there's no addition in here. So that tells me that this is actually my final solution. There's no further way to simplify that function because there's nothing being multiplied to the entire inside. Compare that to here. I actually have 3 things happening. I have a 6, an x, and a 5. The 6 is being multiplied. The 5 is being divided. So I can take the division, ln of 6x minus ln of 5. And that's one possible step. But I can also take the multiplication that now exists in just the first term and split it apart. Ln of 6 plus ln of x minus ln of 5. Giving us a way to write this function in 3 separate terms, since it has its operations being done to all the components. If you have one operation inside the function, it's like 6x, then you can split it apart. Note that none of our rules deal with addition or subtraction, so usually if you see addition or subtraction, that's probably indicating a stopping place. All right, D, the hardest problem we have. So I'm going to start by splitting this using division. This is going to become ln of x squared plus 3 squared minus ln of x cube root of x squared plus 1. Now, there's still more operations that I can do. For example, I have a power being applied to everything, so I can move that power up front. So 2 ln of x squared plus 3. On this one, I have a power being applied, but before there's a power, there's a multiplication sign. And so I have something being multiplied to something else. So according to our second property, I can take those two and split them apart. Now, I'm going to put them in parentheses because remember, these two are together. So this becomes ln of x plus ln of the cube root of x squared plus 1. Since the negative sign was being applied to the ln of both terms, it has to be applied to the separate terms as well. Now I could, of course, distribute that through, which is what I'm going to do in a second, but just note that it has to apply this negative to everything in this top term. Because the negative is being applied to the whole thing up here, it has to continue to be applied to the whole thing down here. Now this first one has nothing left to do, because I have x squared plus 3. The plus is separating these two terms. Since there's not just multiplication, or just a power being applied to the entire interior, I cannot use 2 or 3, and there's no division, of course, so I can't use 4, and there's no 1, so I can't use number 1. So this tells me that this first term is completely expanded. Ln of x squared plus 3. Okay, distribute the negatives. This becomes negative ln of x. Ln of x cannot simplify any farther because there's nothing, again, being multiplied, powered, or divided. But this last term, there is something happening. We have a radical, and we can rewrite this radical as a 1/3 power and then bring it out front. Since again, they're being separated by addition and subtraction, this is the final solution, the one piece that is left whenever we finish this problem. This is referred to as logarithmic expansion, or expanding the logarithm, and it's the primary part of your homework assignment. I'm going to take a look now at one of your homework problems. Let's see. Use the properties of log to expand. So let's look at something like 28. Why not? This is number 28 in your text. 28 says we have the natural log of 3e squared. Okay, so from here, I can take that function and split it apart into two forms. The natural log of 3 plus the natural log of e squared. Now the first term is just a natural log of 3, so that actually can stop right there. And the second term has a power of 2, so I can bring the 2 out front and do ln of e. For now, that's going to be our stopping place. There is one more thing we can actually do, but for now we haven't talked about that property. So let's go ahead and go back and continue with our notes. Okay. The definition of E. So, how do we define E? Now, in algebra, when we talk about E, it's kind of just assumed to be a number. It's 2.7178 or something like that. 2.71828. Sorry. It's in the textbook right there. But calculus has a great definition of it. Calculus states that the natural log of E is equal to the integral from 1 to E of 1 over t dt. And that's 1. So if you graph a logarithmic function, you'll see that it comes up to being very strange values. They're very rarely nice values. But E is the one time it's going to be nice. It's the one time we're going to get something like here, where it actually equals 1. And it's not in a nice place. It's at 2.71828. And so ln of E is always equal to 1, which means there's actually one more step we could take on to number 28 that we didn't finish. So if I go back to number 28, if ln of E is 1, that would mean that we have 2 times 1, which means the solution is actually ln of 3 plus 2. And that's it. So this is the definition of E. In other words, if we look at this in terms of the calculus definition, this tells me that ln of E is defined as the area between 1 and E of 1 over t dt. In other words, that area between 1 and E is 1. If we go back and look at that function right here, this tells me the area between, this blue here, between 1 and E, this area is equal to 1. Notice it's not a nice shape. And so it's really important that that weird shape has a nice value as a solution. And so this is how we define E. E is this one special number that creates this nice, easy to find solution of 1 as the answer for the area. And if you want to know where the area would be 2, it's not 2E. That's not how this works. The area in this case is defined only between these two values. And so E is the one special value that's defined as the area between 1 and E of this exponential function of 1 over x. Now, let's talk about how to do a derivative and how to do an integral of these functions. To start with, we're going to focus primarily upon the derivative piece. So, let's look at some definitions. Like I said, the vast majority of your homework is dealing specifically with those properties, so make sure to get extra practice on those properties. If you find you're struggling with them, you can always look online and look up expanding logarithmic function practice, and it will come up. Okay, so to finish the day, Theorem 5.3. Theorem 5.3 is defined as the derivative of the natural logarithmic function. Okay, there are two parts to this, as you can see in the text. Part 1, the basic derivative. The derivative with respect to x of ln of x is equal to 1 over x, defined when x is bigger than 0. This does not work if x is less than 0. If x is less than 0, it changes. And so this is the first piece. So if you just have the derivative of the natural log, it's easy to do, 1 over x. However, that's not the only thing that can happen. And here we actually have a written version of the chain rule. If I have the derivative with respect to x of ln of u, in this case, u is supposed to be some function with respect to x. Okay? it is going to be equal to 1 over u times the derivative of u with respect to x, or 1 over u times u prime, or as we prefer to call it, u prime over u. So these are the two big ones for your homework tonight to understand. But before we go any farther, it is very important to note that it is much easier to do this second version if you've already expanded as far as you can to get a nicer version of the problem. So let's take a look at the 4 examples they have in the text. And discuss how to take these derivatives. So the first one, d dx of the natural log of 2x is equal to. So if we follow from our second theorem, part of the theorem, theorem 5.3.2, it would say that what we have to do is the interior is acting like our u. So how do we write this? We would do u prime over u. So in this case, my u is 2x, u prime is 2. It's the derivative of u with respect to x. So that tells me that we end up with 1 over x as our solution, which I think is kind of unique, because what this tells me is the derivative of 2x is basically equivalent to the derivative of just x, which I think is neat. B, the derivative with respect to x of ln of x squared plus 1. Notice how this can't be expanded any farther. So this is actually a good place to leave it. And so what I'm going to do now is I'm actually going to take the derivative. So again, it's going to be u prime over u. In this case, this piece is going to be my u. So on the bottom is going to go u, x squared plus 1. On top is going to go the derivative of the inside, which is 2x. Again, you'll note that up here, this is essentially just a chain rule. So if this can be simplified any, I should, but in fact, this is as simplified as it goes, which tells me that's the solution. For C, we have x ln of x as our function, d dx. Okay, this is where it's helpful to remember some things from, previous chapters. We have here the product rule. So this tells me is I have to use the product rule, which states left d right plus right d left, where in this case this is my f and this is my g. So left is just x. The derivative of the right hand side, the derivative of ln of x is 1 over x, plus the right, which is ln of x, derivative of the left, which is 1. And then I simplify. X times 1 over x is going to be 1, provided that x is bigger than 0, which it should be, because that's how we define a natural log, plus ln of x times 1 is just ln of x. There's nothing else to simplify. Here's our function. Okay. D. For D, we have d dx of ln of x to the third power. At this point, we have to do a chain rule. So we have up here g to a power. Remember, to take the derivative of this, we have to take the power rule first, and then times by the derivative of the inside. So g prime. This would tell me that this is supposed to be 3 ln of x squared. So I do the derivative of the outer portion first, so the power of 3 becomes a 3 out front, dropping to 2. And then multiply that by the derivative of the inside. The derivative of the inside is ln of x, which means the derivative is 1 over x. And I could rewrite this as 3 over x times ln of x squared, or some variation on that, but that is our solution. Now, the more difficult ones combine together the logarithmic properties and these theorem from 5.3. These are the ones that are the most difficult in your homework tonight, because you have to get the part done with the properties before you can bother trying to do what's inside of them. So let's take a look at the next example in the text. In the text, we have the natural log of the square root of x plus 1. F of x equals this. And it wants to know what's the derivative. So the derivative with respect to x of the natural log of the square root of x plus 1. Well, I could attempt to apply the previous rule, but it gets real frustrating to do so. Because if I try to do that, well, I'd have to sit there and then be able to take the derivative of the inner piece and multiply that to the derivative of this outer piece. It gets real nasty real fast. It is so much easier if we rewrite this first, and it will actually save a bunch of simplification later. So I will showcase how to do this with the properties first, and then afterwards I'll showcase kind of how to do this using the chain rule. And I promise you the chain rule is worse in every conceivable form. And they're supposed to get the same answer. So please use the properties, okay? So first thing I'm going to do is I'm going to rewrite this function. So this would be ln of x plus 1. Remember, radicals are just powers of a half. Next, the power of the 1/2 can then move out front. Because it's a 1/2 being multiplied to something, it actually will not do anything, meaning I can actually think of it as outside the derivative as well now. And this means I just have to take the derivative of ln of x plus 1. Now, ln of x plus 1, I can think of using theorem 5.3 part 2. So I can take the derivative of the inside and do essentially, to this piece, u prime over u. So let's do that. U prime would be, derivative of x plus 1 would be 1. Over u would be x plus 1. And so I end up with a very simple solution, 2x plus 2. Or you could leave them separate if you really want to, but I like it that way. Look how simple and straightforward that is. Let's now compare this to if we try to do this with a chain rule without using the properties. We will eventually get to the same answer, but I promise you it's going to take a lot longer, and it's going to be a lot less fun. So, to do this, we now have this big term, the square root of x plus 1, as our u, which means that our u prime is going to be, so this would be x plus 1 to the 1/2 power. It would be 1/2 x plus 1 to the negative 1/2 power. Okay, so if I was to rewrite this function, this would mean that this derivative is equal to, so u goes on bottom, so that would be the square root of x plus 1. And on top would go the u prime, which is 1/2 x plus 1 to negative 1/2. And at this point, you're now tasked with simplifying. If you don't remember how to simplify this, then maybe you want to learn the new period, okay? Learn this new material. Because if you learn how to rewrite it, well, look how much simple this is to simplify. You just take 1/2 times this function and you're done. But with this one, I have to remember that the 1/2 power is going to drop to the bottom. The 2 is going to drop to the bottom, so this becomes 1 over the square root of x times x to the 1/2 power. I have to then remember that 1/2 power and 1/2 power together makes a whole power. And it's just a lot more work to get from here to here than it is to get from here to here. It's so much easier and nicer. And the derivatives are easier, right? I mean, derivative of 1/2, well, that just pops out front. Derivative ln of x plus 1, that's easy. You just do the rule for 5.3.2, u prime over u. And so it's so much easier to do it with the properties as opposed to trying to force it to work using the chain rule. Now again, the chain rule worked. It got me to the solution eventually, but I have to know more advanced properties and apply them correctly to get that solution. If I make even a single mistake in here, I will get a wrong solution. It is much less likely to make a mistake here, and the steps themselves are easier to do. So use this top one. I'm not threatening you to use it to say you have to, but use it. Okay? Now, in terms of what we have for our homework tonight, that's the end of the material. Relatively short lesson today. We'll be continuing 5.1 tomorrow, talking about the more complex differentiation, where you have to kind of double up on your differentiation by using the properties and then using something else. But that is pretty much it. For your homework tonight, let's not forget, our homework was page 331/355, 7 through 35 odds, 39 through 53 odds. I skipped the one in the middle because it deals with using a calculator, and I don't know which calculators you guys are using. So make sure you get that information. Make sure you get your homework. It will again be due on Saturday. We'll have a new assignment posted tomorrow to finish out 5.1 and possibly even to start 5.2 because 5.2 is kind of fun. So that'll end it for me. I hope you guys have a good rest of the day, and I'll talk to you guys tomorrow.